As mentioned, my name is Larry Garfield. You may know me online as Krell. If you want to make fun of me on Twitter, that's where you do so. I highly encourage it. I'm the Director of Developer Experience at Platform SH. We're a continuous deployment cloud hosting company. I'm also a member of the PHP Fig core committee. Everyone familiar with Fig? It's kind of like the United Nations of PHP, with all the good and bad implications that has. If you want to know more, we are having an open meeting today right after lunch in track 3. So if you're interested in Fig, its work, what we have done, what we are doing, stop on by. We actually have elections open right now for the next round of core committee members. And for those who get the joke, I am in fact PSR8 compatible. Who actually gets that joke? I never know. Okay, a couple of people. Okay. This is a computer. This is a very old computer, specifically an IBM System 360, Model 20. System 360 was originally announced in 1964, and it was intended as the world's first complete range of compatible computers. What does that mean? Before this, every model of computer was unique. Every individual model of computer had its own architecture, its own system, its own programming, and software was not portable between them in the slightest. This was the first time that you had a line of multiple computers of different builds that you could run the same software across multiple models. This is really cool. This is a really good innovation. In order to make that work, you needed to have, for the first time, a distinction between architecture and implementation. You needed to distinguish between how the system is designed to interface and how the system actually works down at the microchip level. System 360 was developed over the course of 2 years because software projects and technology projects always run late. But it shipped for over a decade. It was one of the most successful lines of computers ever made. And this split between architecture and implementation, this flexibility, was incredibly powerful and incredibly useful. For example, it was compatible with the standard reel-to-reel tape drives, they have to go the same direction, reel-to-reel tape storage systems, as well as this crazy newfangled technology called spinning disks that could store like thousands of bits of information in something only about this tall. It's really cool, like the data density these things had. System 360 had a huge impact on the technology landscape. For example, 8-bit bytes. Why are bytes 8 bits in size? Because System 360 decided they were. Before that, it was common for different computers to have different size bytes. You don't think of that anymore, but bytes used to be variable size. And one fun story, the most common standard before this was 6 bits to the byte, which didn't actually give you enough characters to have both uppercase and lowercase letters. So designers working on those systems had to decide, all right, do we have all uppercase or do we have all lowercase? And they did research and found out that all lowercase is easier for people to read than all uppercase. And they took this to their manager, and the manager said, but we're IBM. We can't have our name in lowercase. And so the standard was all uppercase for the next 30 years. Because ego. But yeah, the 8-bit byte comes from System 360. The idea of addressing memory by byte offset only. In many earlier systems, you could in fact address memory down to the bit level, which was not actually a good thing, because you could do some really weird things then, and weird in a bad way. It also established ABCDIC, which you've probably not heard of because no one else used it and they use ASCII instead. So, can't win them all. System 360 still lives on, however, in the IBM Z-Series mainframe computer, which is still backward compatible for a lot of the original programs written in the late 60s. Are any of your computers compatible with code written 40 some odd years ago? And by the way, these things do run PHP. Now the lead team on this project was these two men, Gene Amdahl and Fred Brooks. Fred Brooks is actually the one who coined the term computer architecture in the first place. After the project was over, the team wandered off to various other endeavors, other projects. Many of them ended up in academia, like you do. And 10 years later, Brooks wrote a book called The Mythical Man-Month, and updated it 20 years later, in 1995. That's what this picture is from. Mythical Man-Month is a collection of essays by Brooks of essentially lessons learned from managing large software projects, both System 360 and others, drawing on both his own experience and academic research at the time of how does one manage large software projects and make them not be a disaster, which is kind of useful. The new edition included a number of additional chapters, including looking back on his earlier predictions or earlier statements around how you should run software projects to say, so these things I was saying, are they still true? And his conclusion was kind of, yeah, they're still true, because humans haven't changed. Technology's changed, humans haven't changed. So it's been another 20-ish years since then. What I'd like to do today is ask, are these recommendations, are these conclusions, are these guidelines he has still valid? Let's find out. Now I'm going to go through this in a somewhat different order and structure than Brooks does. I'm actually going to cover only about half the book. One thing that I will note he doesn't get right is extreme overuse of male pronouns for no good reason. So ignore that part, please. But I think we'll find the rest of what he says holds up pretty well. Who's heard of Brooks' Law before? A few people? Who's heard of this law before? Wow, not enough people. Well, now you have. Adding people to late software projects makes them later. Why? There's a number of reasons. One, communication is hard, let's be honest. Why is communication hard? Because the more people you have, the harder communication becomes. Because the more people you have, the more communication channels you have. When you only have 2 people on your team, you only have 1 conversation to have. When there's 3 people on the team, there's 3 conversations. 4 people, there's 6 conversations. 5 people, there's 10 conversations, and so on and so on and so on. The number of pathways you have to keep track of goes up faster than the number of people on your team. And there is, in fact, a mathematical formula for this. That's what it is. Don't bother memorizing it. That's not important. What's important is the fundamental idea: the more people you add, the more conversations you have to have, and the longer it takes to just keep everyone on the same page. Just coordinating people is harder the more people you have. It's also a problem that tasks are usually not parallelizable. It would be great if you could just split a task up into 1,000,000 pieces, do it all quickly, and be done. Most tasks don't work that way. Now, this is a management talk, so I have to have a Dilbert strip in it. I hired all of you because the project will take 300 days to complete. There are 300 of you, so I want you all finished by 5 o'clock, you're fired. Doesn't actually work that way, does it? Although I'm sure there are managers who wish it would, it doesn't actually work that way. Why? And it works, it is true for unskilled tasks too. Why? Because sometimes you have limited resources. You may not simply have enough computers for 300 people. You may not have enough chairs for 300 people. You may not have enough server capacity for 300 people. You may have different skill levels. The person who's really good at SQL and the person who's really good at CSS are not the same person. And you can't just throw 100 SQL developers at CSS and expect it to get done quickly. It doesn't work that way. Believe me, I've tried. You can also have tasks that block others. This task just, you can't actually write something that uses this API until the API has been designed and built. Maybe you can mock stuff out, but that's not actually going to give you a real experience of using that API. You're not going to know what the timing is like. You're not going to know what the latency is like. A couple of years ago, I was helping friends. I'm from Chicago, and I was helping some friends move from Chicago to New York. And so, like you do, they had a bunch of their friends over, ordered a bunch of pizzas, and we packed up their apartment to put it all into a moving van. And they had somewhere around 100 boxes or so, which means they need 100 friends, and they'll be done in about 5 minutes, right? Who's helped friends move before? Does it ever work out that way? Why? We have one elevator in the building. We only have 2 dollies. You can only fit so many people into the moving van at the same time. The people packing the boxes need to know what things can go on top of what. The people packing the moving van need to be the same people who are going to be there to unpack it at the other end, so they know which boxes are which. Even if they're labeled, you still need to keep track of which type of box is which. Just fundamentally, you can't just throw people at the problem, even when it is a basic manual labor task. One thing we never did figure out, though, is why anyone would want to move from Chicago to New York, but I'm biased. Quite simply, people and months are interchangeable commodities only when a task can be partitioned among workers with no communication among them. Because once you have to communicate, you have to coordinate. And in fact, adding more people to a project increases the cost at times. More Dilbert. How long will this project take if I add 2 more people? Well, add 1 month for training, add 1 month for extra complexity, and 1 month to deal with their drama. Because people. Why? When someone joins the project, they know nothing. It's going to take time, someone else's time, to train them and teach them on the project, tell them how it works, where the bodies are buried, explain how the code works for the parts that aren't documented, because of course there are parts that aren't documented. Even if you do a good job of documenting, it still takes time to learn the system. Excuse me. And then of course, that time is time that someone else is not spending working. And then of course there's their drama, because more people, more communication, more opinions to keep track of, and so on. So can you add people? Sometimes. I would argue, if you add people to a project early, then you can absorb that additional cost, and they can ramp up, and by the time they're ramped up, they can actually be useful. It really depends on how early you add them and the number of swim lanes on a project. Swim lanes is a concept out of Agile, and roughly corresponds to the number of parallel parts of the code that you can work on without bumping into each other. And different projects will have a different natural number of swim lanes. Sometimes the swim lane is 1, sometimes it's 2 or 3. Very large projects could have swim lanes of 7 or 8. It's the number of times you can have different people working and their commits are not going to just bang into each other, basically. I would argue the number of developers you want on a project is the number of swim lanes plus 1. That gives you extra capacity for someone to go on vacation, someone doing code reviews, someone to get sick. That's the maximum number of developers you want on a project. If it's a very large project with a lot of swim lanes, maybe you could add swim lanes plus 2. But adding more people in that is just going to make things slower. Things just take time. Now note I'm saying here number of developers, not number of people involved. So this is not counting your project manager, your product owner, and so on. The number of people touching the code base at a time is the number of swim lanes plus 1. This is even found in hardware too. This is Amdahl's law, same Gene Amdahl we talked about before. And again, ignore the actual math. The point being, this is an equation for the number of CPUs you can throw at a problem before you get diminishing returns. And the more parallelizable the product or the problem space is, the more CPUs you can throw at it and actually get a benefit. But eventually, even with something that is 95% parallelizable, the task is easy to split up into lots of different pieces, throwing more than about 1,000 CPUs at it, you're not really getting any benefit, because there's still coordination overhead of keeping track of all of those different pieces and synchronizing them. The vast majority of software projects, the process of actually writing them, are nowhere near the 95% parallelizable. They're more like 5% parallelizable. So what do you think? True? Still true? 40 some odd years later? Yep, I'm going to say yes. This totally fits my experience. I mentioned before I'm only talking about half the book or so. The first time I gave this talk, I was whining on Twitter, like you do, that there's just too much material in this book to give in one talk. So someone helpfully suggested that I get a second speaker on stage to give a talk on the other half of the book at the same time. Yeah. Of course, we all work, or most of us work in open source in some capacity, or use open source projects in some capacity. Do we know any projects that like to solve problems by just throwing warm bodies at a problem? I used to be a Drupal developer, I can talk about them. Oh dear. What's the combinatoric number for that? What should we learn from this? Next up. Who likes doing estimates? That's what I thought. Why are estimates always so wrong? There's a lot of reasons, but one of the key ones that Brooks talks about is this. When you as a developer give an estimate, you're giving an estimate for this, for a proof of concept that handles the happy path. That's what your brain thinks. You're looking at how long does the basic version take. If you actually want a product out of it, which means something actually useful that handles all the edge cases, the error cases, is well tested, it's good documentation, you're looking at 3 times as much work. 3 times as much work as producing the proof of concept to turn it into something actually real and useful. If you want it to be something others can build on, you want it to be extensible, you want a programming system that people can leverage, that takes 3 times as much work as just building the base proof of concept. Which means if you actually want a real stable product that people can use, that's tested and documented and handles all of its error cases, you're looking at 9 times as much effort as the proof of concept in your garage type project. 9 times as much work. You don't estimate for that because you don't think about those. You're a developer, you think about this part. Brooks also notes that a substantial bank of test cases exploring the input range and probing its boundaries must be prepared, run, and recorded in order to have a viable, stable programming product. What does that mean? It means automated testing was already a thing in 1975. What's your excuse? Note, this does not mean that it takes 3 times as long if you're writing tests. It takes 3 times as long to find all the bugs that tests find, or to fix all the bugs that tests find for you. The bugs are going to be there no matter what. It's a matter of finding and fixing them via tests. I also want to know, how fast can you code? Just think about that. How fast can you produce code? You're wrong. Because I didn't give you enough information. Extrapolation of times for the 100-yard dash show that a man should be able to run a mile in under 3 minutes. The current world record is 3 minutes 43 seconds. Because you cannot maintain that same speed for an entire mile. You can't sprint a marathon. In fact, what research found was that the amount of effort to produce more code is based on a power of the number of instructions already in the code base. Translation, the more code in the code base, the longer it takes to add more code to it. It is harder to add more code to a larger code base. Why? Because there's more things that can go wrong. There's more possible interactions. This is true even if there's no communication between people. There's more interaction points internally in the code. Your brain can only hold so much code in it at the same time. If you want to figure out, okay, what's the impact of this change, the scope that it may impact, the larger that is, the harder it is for you to reason about, which means you're going to get it wrong and introduce bugs and you have to go fix those too. Bigger code bases are harder to add more code to. In fact, one study found that, I'm not quite sure what very few, some, and many mean in this case, but a person can add 10,000 instructions to a code base when there's very few interactions, for their definition of very few. If there's a decent number of interactions, they can only add about 5,000 instructions per year. If there's an awful lot of interaction, almost an order of magnitude fewer. The more complex the code base, the slower it is to add code to it. Now, what does large mean here? In this study, large meant 25 programmers and 30,000 instructions-ish. This should be a good indicator you want decoupled code. Now, I said instructions here, and someone's probably going to call me out and say, but you're talking about assembly here, instructions. What about in real code? Later studies found that in PL1, which was kind of the C language of the 70s, the same curve happened. You had the same equation for number of statements instead of number of assembly line instructions. What does that mean? It means a more expressive language does give you more productivity. You can get more done in a more expressive, more powerful language than in a less capable language. This is true. But no matter how good your language, the larger the code base, the slower it is to add code. What do you think? True? This feel right? Seeing people nodding? Yep. I'm going to agree. Totally right. One catch, though. We said large is 25 programmers and 30,000 instructions. How many lines of code are in Symfony? What should we learn from this? Who likes writing documentation? Okay, sponsors looking to hire, the people with their hands up are the ones you want to hire. Planning and documentation, Brooks argues, are the same thing. These go hand in hand. You want to be writing your documentation up front. Why? Because only when one writes do the gaps appear and the inconsistencies protrude. The act of writing turns out to require hundreds of mini decisions, and it is the existence of these that distinguish clear, exact policies from fuzzy ones. Huh? You're rubber ducking with your word processor. This happens to me all the time. I used to work as a consultant, and all the time I'd go to a client on site with my team. We'd spend 3 days talking to them, collecting information, figuring out what it is they want, what it is they need, not the same thing. Come up with a plan. We'd go back to the office. I'd sit down and start writing it out and planning it in a Google Doc, describing in prose what we're going to do, and describing in architectural diagrams what we're going to do. And every single time I came up with, we didn't talk about this edge case. What should we do here? What happens when there's no data here? What happens on leap years here? Because they kept asking us to do calendars, and dear God, I hate calendars. Writing down and trying to explain back to a document what it is you're going to do helps you figure out that you don't know what you're going to do. The crucial task is to get the product defined. Many failures concern exactly those aspects which are never quite specified. If you don't know what you're going to build, you can't build it well. If you haven't tried to explain in detail what you're going to build, you don't know what you're going to build. But that manual or written specification is a necessary tool, but not a sufficient one. The code is your formal definition, and that's a precise description of what you're doing. It does not tell you why. No matter how well written your code is, it does not tell you why it is. That's what documentation is for. That's what planning is for. And Brooks argues for top-down design. What does that mean? Architect the system first, end to end. Break that architecture down into discrete pieces and refine those layer by layer and keep recursing until you have a plan for how your system is going to be built. Then you can implement each individual module that you've come up with, debug them individually so that you can actually find bugs in them. And as you are developing, you can inform back up and modify the architecture as needed based on your experience building each piece. Basically, divide and conquer, which is the standard approach to anything in science or math, which is programming. When you have a problem, break it down to smaller pieces that are easy to solve, then put it back together again. He also says, plan to throw one away, you will anyway. Version 1 is always crap. Why? You don't actually know what you need to do until you've done it wrong at least once. Who's heard the old joke that, is there anyone here from Microsoft? Can I make fun of them? All right, there's an old joke, Microsoft doesn't get anything right until version 3. Yeah, that's not just Microsoft, they're the joke, but that's everybody. Because, yeah, your first version, you don't know what you're doing yet. Now, at this point, I'm sure there's someone in the room who's going to go, Larry, you're talking about waterfall. We all know that's terrible. And in the second edition, Brooks said, yeah, that kind of is waterfall, isn't it? That's not great. All right, let's tweak it. Design top-down, but implement iteratively. What does that mean? Once you have your plan, start by building an end-to-end skeleton. This is a not necessarily complete, but still functional and will compile system. It doesn't necessarily do anything useful or much useful, but it does give you a baseline. And then always make sure it works. Always be compiling, or in PHP's case, running, whatever. And once you have this working baseline, grow modules into place. Implement new functionality, replacing stubbed out pieces, and as you go. And make sure that at every stage of the way, you have a system that may not be useful yet, but it still runs. It still passes tests. If you need to just rip out a piece and throw it away, cool, do so. If you need to tweak a piece, cool, do so. Now note, building this skeleton could take a long time. This could be half your project, just building that baseline. That's okay. This should look familiar to people. It's called refactoring. Refactoring is the art of throwing it away, throwing your first version away a little bit at a time. But if you still have a complete running system, or a functional running system at least, the entire time. But this approach necessitates top-down design for this top-down growing of the software. Building individual pieces in isolation and then hoping they'll work when you plug them together is not going to work out well. Building the framework and then plugging pieces into it as you go, that works a lot better. That said, common sense, if not common practice, dictates that one should begin system debugging only after the pieces seem to work. Architect top-down, debug bottom-up. Unit tests first, in other words. Now this should also look familiar, and the same person as before is probably going to start shouting, but Larry, isn't this agile? Who's seen this picture before in some form? Who thinks this is actually a good picture? This is terrible. This never works. Who here has managed to successfully build a bicycle into a car? I never have. In this setup, you are in fact throwing it away twice. You're throwing away your entire system twice. Don't do that. Don't do a complete rewrite. We know those are a bad idea. Instead, you do this. You don't start with a useless individual piece. You don't start with something that is not going to work for what it is you're trying to build. You start with a baseline that functions. It's not done, but it functions. And then you can add pieces to it, and add pieces to it, and change the paint, and change the hubcaps, and possibly change the top. But your A-frame, your baseline of the system, hasn't changed. You start with a skeleton that supports your end goal, and then build from there, with decoupled components so that you can swap out the wheels when you need to. Note, this means you are not going to build the most user-important feature first. You're going to build the foundation first. If you're building a house and the customer says the most important thing for them is to have a fireplace on the second floor, are you going to build a fireplace on the second floor first? No! You're going to start by building the basement and pouring the foundation. Because if you don't, you won't have a second floor on which to put a fireplace. Same in software. The most important thing that the functionality the user wants is not the first thing you build. The first thing you build is the baseline that's going to let you eventually build a good thing the user wants. What do you think? True? See people nodding? Yep. I'm going to give Brooks 2.5 out of 3 at this point, because he had to revise it a bit. Brooks gave a presentation in 1986 at a conference called No Silver Bullet, which turned into an essay in the updated version of Mythical Man-Month, in which he talks about how there is no silver bullet that is going to fix all of our productivity problems anymore. And Brooks draws a distinction between essential complexity and accidental complexity. Essential complexity is this problem space is just hard. The problem space itself, the logic, business logic itself is complicated. As opposed to accidental complexity, which is my computer is too slow, and so I can't work very effectively. Who's worked on an e-commerce system of some kind? Yeah, e-commerce is hard. Why is e-commerce hard? Not because the e-commerce software is bad. Some of it is, but that's not the point. E-commerce itself is complicated because tax law is complicated, because shipping is complicated. Nothing you do will make those not complicated. You can only paper over that and make it look easy, but it's not. Accidental complexity is my software is crap, which also happens, but that's a different matter. The hard part of building software is the specification, design, and testing of the conceptual construct, not the labor of representing it and testing the fidelity of the representation. The design is the hard part. Remember, when Brooks was working on System 360, the way you tested your code to see if it worked is you took your stack of punch cards, walked down the hall to the elevator, went down 5 floors to the basement where the room with the computer was, because you only had one, handed it to the computer operator, who would put it in line and eventually put it into the feeder and it'd go through the computer and it would barf, and you'd come back 3 hours later and they'd hand you a stack and says, it errored on card 417. Have fun. And you'd carry the stack of punch cards back up to your office and stare at card 417 while you figured out what was wrong with it. We are a long way from that. Debugging by punch card is not what any of us are doing anymore. I certainly hope. Anyone here still debugged by punch card? Good. You don't want to. There is no single development which by itself promises even an order of magnitude improvement in productivity, reliability, or simplicity. There's room for improvement, but we are not going to get productivity improvements anymore that's on the level of replacing stack of punch cards with computer sitting on my desk with an IDE that I can just step through individually. There are still improvements we can make, programming techniques, programming languages, and so on. But order of magnitude, something that's going to make us 10 times more productive, those don't exist anymore. We've already handled all of the low-hanging fruit. So how do we attack essential complexity? How do we've solved the accidental complexity enough. How do we make the actual fundamental problem we're trying to solve easier? Brooks offers a couple of options here. Rapid prototyping, where we grow a system organically based on user feedback, so we don't guess wrong. Buy versus build, and mentoring better architects. We already talked about the first one, so I'm not going to cover that again. So for buy versus build, Brooks points out that the most radical possible solution for constructing software is to not construct it at all. Well, think about it. In the 60s and 70s, a computer cost $20 million. Spending $50,000, euros, well, they didn't have euros, lira, on custom software for it is a rounding error in your budget. You don't even notice. Your accountants can't find it. These days, you can get a computer this big for 10 bucks that is a fully capable development system. Just plug it into a monitor. I have one. It's kind of cute. The software is now the expensive part. If you want to save money on your system, you have to write less software. How do you do that? By reusing software and their components. Why would you, if you need a spreadsheet, why in the world would you write a new spreadsheet? You've got Excel, you've got schools sheets, you've got, I think there's something else still on the market. It's a solved problem. No one in their right mind is going to write a commercial spreadsheet from scratch or custom build one for yourselves. If you need a CMS, why would you write a CMS completely from scratch at this point when there's 30 on the market just in PHP that are all battle tested and used by literally millions of people? If you need a web server, you've got Apache, you've got Nginx, you've got IIS, you've got the standard library in Go. Why would you write your own web server from scratch? You wouldn't. It's easier to just take these pieces off the shelf and use them. Does this sound familiar to anyone? It should. Brooks just described open source. He didn't use the term, it didn't exist yet, but that's exactly what we just described. The way to be more productive is to write less code, which means the way to be more productive is to reuse more code. Open source is the #1 productivity improvement of the last 20 years. This gigantic library of code that we can share and reuse and repurpose as needed. Nothing in the entirety of my career has had a larger impact on improving developer productivity than the ability to share code easily and effectively. If you are not using at least 90% open source in your applications, you are burning money. You are simply throwing money away. The other thing that Brooks recommends is growing great designers, because software construction is fundamentally a creative process. Note a shift here, architect to designer, from the 70s to the 80s. Study after study shows the very best designers produce structures that are faster, smaller, simpler, cleaner, and produced with less effort. The difference between the greats and the average approach an order of magnitude. Oh my God, 10x developer discrimination, privilege, blah, 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 blah. No. No one is going to, the great developer is not going to be able to produce 10 times as much code per hour as a junior. And if they do, you really don't want to see that code. But a great designer will design a system that requires 10 times less code to be written in the first place, or code that is 10 times less likely to have secret hidden bugs in them. Software architecture is much more like graphic design than it is an engineering discipline. There's a gestalt to it that you simply don't have in engineering. Architecture is a separate skill set from programming. You can have someone who's a great programmer and only a mediocre architect, and someone who's a great architect and kind of a so-so programmer. And Brooks argues, architects, designers, need recognition on equal level with management. It's not engineers and architects and managers. You have a technical track and a management track, and they have to be parallel with each other. And whatever that means in your company in terms of salary, in terms of prestige, in terms of who has corner offices, the technical leads should be at the same level as management because they are just as important as a good senior level manager. How do you do that? Through mentoring. Identify candidates early on who seem to have good design and architecture skills, who may not be your senior engineers. This is a different skill set. Someone can be an okay engineer and a really good architect if you train them properly. Really good at solving the large scale problem. Give those people a career mentor. Active mentoring. Give them someone to work with who can help train them. Give them apprenticeships. Give them formal education in software architecture at classes. Give them solo work to work on. Send them to conferences like this one, where they can collaborate with other designers, other architects in the field. All of these are things the design world does. The graphic design world, the product design world, they do all of this kind of stuff. Why don't we? We should. because this is how you build better designers who can then produce a better system. True? Yep. Yep, he's right on this one too. And finally, Brooks' strongest point, conceptual integrity. The conceptual integrity of the product as perceived by the user is the most important factor in ease of use. As perceived by the user. You want the user to have one mental model that they have to keep track of. Only one set of nouns they have to keep in their head at a time. If they have to think about the program one way over here and a different way over here, they are going to get confused. Which means you need to have one mental model throughout the entire system. Ease of use is not just a question of how little documentation do I need to read. Ease of use is a factor of how much you can get done versus how much conceptual complexity I have to think about in order to get it done. A complex 3D rendering program like Blender or Lightwave is an incredibly complex piece of software. You need to take a class to learn how to use this stuff. It's not something you can just pick up yourself in an afternoon. But the stuff you can do with it, I mean, have you seen those amazing animated films that Marvel's been putting out? You know, the Avengers movies? Those are 3/4 computer graphics. And they look fantastic. Those have a high ease of use for what you can produce versus the complexity. At the other end, Windows Notepad has about 3 functions in it entirely. That's about all it does. But you can learn it in about 4 seconds. Am I saying that Notepad and Blender have the same ease of use? Maybe, relative to what you can do with them. Insert joke about Vim here. A lot of Vim users in the room, I guess. Simplicity and straightforwardness, however, proceed from conceptual integrity. That ease of use, you want to lower that complexity in order to make it easier to use. In fact, conceptual integrity, Brooks argues, is the most important consideration in system design. It is better to have a consistent, clear design than to have more features. See also iPhone. The original iPhone sucked from a feature standpoint. It didn't have copy and paste, didn't have an app store, didn't have high-speed internet. It had 3G, if you were lucky, maybe. The few things it did, however, it did extraordinarily well. And they sold millions of them for a reason. But conceptual integrity of the product not only makes it easier to use, it also makes it easier to build and less subject to bugs. That same one conceptual model concept applies to the developers just as well as the users. If you want your developers to be able to keep track of the system they're building, they should have one mental model, one conceptual picture of how the system works, one set of nouns, one set of APIs that they end up using rather than 7 that are kind of slightly different. You may have heard this term from the DDD people, ubiquitous language. Same concept, just a bit older. So how do we have a good conceptual integrity in a system? Brooks argues you have that through smart division of labor. What does that mean? The design must proceed from one mind or a very small number of resonant agreeing minds. You want to have one clear vision that is directed for how the system works. How do you do that? Brooks offers 2 possibilities. One is a surgical team, where it's modeled on actual surgical teams in hospitals, where you'll have a surgeon working on a patient, and she's standing there cutting and doing whatever else, and there's someone over here who would say, give me a scalpel, give me a sponge, ham sandwich. You have someone over here who's making sure the lights are just right. You have someone over here who's wiping sweat off the surgeon's brow. You have someone over there who's keeping the clients away, the family away, so that the surgeon can do everything with 0 distraction. I've never actually seen this happen in software, so let's not talk about that again. Would be a nice idea, but I've never actually seen it work. The other is to split the architect from the implementer. Have someone architect and someone else build that architecture. This is not monothink, but it's avoiding conflict think. you have one or a very small number of people who design the system, and then you have people who build the system, and those are different people. The people just building the system don't get to redesign it on the fly as they go, because that is how you get a mess. The architect is the user's agent. It is their job to bring professional and technical knowledge to bear in the unalloyed interest of the user, as opposed to the salesman, fabricator, and so forth. User's agent. The architect is there to make sure the system works and is understandable to the end user. And I'm sure, again, that same person is going to say, but Larry, that's cathedral design, that's aristocracy, that's top-down, cathedral in the bazaar, we want the bazaar. Cathedrals are still standing. In Verona, you've got a number of really nice cathedrals. I've seen some of them, they're fantastic. Those had an architecture that was planned out from the beginning and took 500 years to build, and they followed the plan. Yes, the art varies over time, but the general architecture of the building was relatively constant for centuries. And that's why they're still standing and why they look gorgeous. I personally love cathedrals. They're just beautiful creations. Look at Apple. Apple has dozens and dozens and dozens of designers, very good designers. But at the end of the day, Johnny Ives is calling the shots. What is Apple's brand design image? It's what Johnny Ives says it is. Google has thousands of people doing design and developments and programming. And at the end of the day, Matthias Duarte is the one who designs material design. Matthias Duarte is the one who says this is what Google's brand will look like. And so you get a consistent brand out of it. If you're working with any modern Unix system, Linux, BSD, Mac, you're using the POSIX standard. Why? Because that's the standard. If you don't follow that standard, things don't work right. You don't like that standard? That's nice. Your code's not going to work right unless you follow the same standard as everyone else. When someone doesn't follow the standard, you see why it's a pain in the butt. We work on the web. You're following HTTP. If you don't follow HTTP, things break. You don't like how HTTP's caching works? That's nice. If you don't follow that caching standard, you're not going to get any good caching. Or worse, you're going to get buggy caching, and that's a bad place to be. These architectures you inherit and you work with because that is what the architecture is. And if it's not followed, things don't work. The architect is responsible for designing watch dials and hands. This is the example Brooks uses. The implementer figures out bells and gears. Both of these are fun. Both of these are interesting challenges. But a good architecture supports both. Anyone have a rotary watch still with watch hands? Few people. Exact same mechanism in that watch runs Big Ben. Runs the astronomical clocks that various cities have. Building those giant clocks is still a fun challenge, believe me. But the basic architecture of hands moving at different rates was set down a long time ago, and you still follow it. But the architect must always be prepared to show an implementation of a feature described, but not dictate the implementation. You have to be able to show developers, I'm designing something for you that I know is possible to build. I'm not just telling you to create anti-gravity or something. But now that we've said, okay, here's what we're going to build, the how, that's the implementer's job. Here's the parameters, go build it. I can't tell you exactly how you should do it. That's your job to figure out. That's your responsibility, not mine. That's your fun place, not mine. This also reduces the communication channels. Instead of having everybody talk to everybody, the architect talks to each developer, and the developer talks to the architect. And now you only have N+1 chains of communication that you have to keep track of, because the architect is the keeper of, well, the architecture. This also lets you divide and conquer larger systems. If you have an especially large system, you have subsystems with their own architects, their own keepers of the design. And they coordinate with the senior-most designer senior-most architect, and then the developers work in their own areas. See also the Linux kernel. Linus does not review every line of code. Linus reviews aggregate patches sent to him by subsystem maintainers who review every line of code in their subsystems. Is this a hierarchy? Yes, it is. And it works. Democratic architecture is known as MUD. I have worked on this system before. It was painful. I've tried to fix the system before. It is even more painful. This is, it does require an ongoing collaborative environment. So you can't have an architect who just designs and walks away. The architect must be there for the whole project, available to help tweak things because you are going to need to tweak things. Do we know any projects that have no clear organization and no clear person in charge, no clear architecture, that end up being kind of a muddled mess of inconsistency? What can we learn from this? How big does a project need to be before all of the stuff we're talking about matters? After teaching software engineering lab more than 20 times, Brooks came to insist that student teams as small as 4 people choose a manager and separate architect. 4. Manager, architect, 2 implementers. Either the manager or the architect can be the lead person in charge. Either of them can be the boss. It doesn't matter, as long as everyone agrees which one is which. Works either way. But a team as small as 4 needs to have someone coordinating the vision. Because as soon as you have 3 or 4 people, you have disagreement, you have cliques, you have different people just making different assumptions than each other, and those are going to bite you. And that's when you need to have someone who is the keeper of the design. So what should we learn from all of this? Software construction is a creative process. It is much closer to design than it is to engineering. When in doubt, divide and conquer is your friend. This is how you solve most problems in any scientific field. How do you do that? You want to build shareable programming system products. Leverage open source, build in components that you can swap out and you can evolve independently of each other. Build divide and conquer into your architecture. That way, when, not if, system requirements change, you can adapt more easily. Decouple your libraries from your framework so that you can do that. You want these independent libraries that you can release, that you can swap out, that you can replace, that you can test independently. But you still want to have top-down design, so that the whole system has a coherent, consistent vision behind it, consistent architecture behind it. And to do that, you need to empower architects to make decisions. You have a person whose job it is to communicate with everybody, to talk to everyone, to take in input from the developers, and decide this is how we're doing it. This is the standard we're going to have, this is the approach we're going to have, this is the architecture we're going to have, and have that stick. Back them up. If you just let everyone do their own thing and architecture emerges, the architecture that emerges will be a pile of mud. Fundamentally, the idea that people knew a thing or two in the 70s is strange to a lot of young programmers. From Donald Knuth, father of the analysis of algorithms and the author of the book, The Art of Computer Programming. What can we learn from this? Grazie mille.